Right, thank you very much. Just a little bit of a technical changeover there, and it's my turn. Now, perhaps I ought to just explain a little bit about the forensic archaeologist. What's an archaeologist doing talking about cleaning and antimicrobial things? Well, my interest has been the origins of disease, and a few years ago I was working on some ancient Egyptian artifacts, carrying out the analyses to find out what the ancient Egyptians did, and it's quite surprising how they got some pretty good ideas on how to deal with infection without really knowing what the mechanism of infection or sepsis or antisepsis really was. So that's where the archaeology bit fitted in, but for many, many years I've had this interest in the chemistry of disease and dysfunction, and it's that I want to talk to you a little bit about this afternoon. It's going to be some fairly deep chemistry. I make no apologies for that. A lot of you are scientists or got a scientific interest in what's going on. I need to explain to you the logic of what's different about microbiome and how it works. And really, I'm going to jump straight into here with the quaternary ammonium compounds. These are not the same as ammonia, you know, the stuff that you get in the cleaner's cupboard. You take the top off and you're holding it at arm's length because, you know, the smell is absolutely horrendous. It's toxic. It's nothing like that. These quaternary ammonium compounds have been around for quite some time, and they've been used for quite important applications. Whenever I go abroad, get on the plane, I take some quaternary ammonium compounds with me because they're superb for killing bugs, especially those coming through the aircon. The important thing about this is the quaternary. An ammonium compound would have a central nitrogen atom which carries a positive charge, hence ammonium. But with quaternary ammonium, instead of having hydrogens attached, we have alkyl groups, usually 2 methyl groups, and alkyl groups as well. One of those alkyl groups could be another methyl, so you could have 3 methyls, or you could have 2 alkyls, say 2 octyl groups, 2 decyl groups. Various sizes, various lengths. The important thing is there are no free hydrogens on there. These are quaternaries. They're a lot safer than ammonia. That is the starting point for the work on the biocides on the microbiome. These quaternary ammonium compounds, as I say, have been used for quite a long time. They're efficacious. They have a very good remnant effect. They're stable. They're very easy to formulate. You can put them into a whole variety of different materials over a wide pH range. They have very little odour, very little taste, so it's quite easy to fragrance them as well. So ideal commercial products. When you compare the quaternaries against various other biocides or effect molecules, you've got quite a nice pH range. pH is operating between 1 and 14. Well, the quaternaries, you can operate over most of that range, whereas other biocide types, the phenolics, phenol of course was one of the very first biocides, if you like, although it wasn't called a biocide then, introduced 150 years ago by Lister and Lemaire, and still used to this day, you know, the carbolic soaps and so forth. Iodine containing materials, you can only use them over a very narrow range, and likewise with hypochlorite or the bleachers, again you've got a restricted range. For cleaning, the quaternaries win hands down, far better than the other materials. They're also low staining. Go and wash your hands with phenolics and you can smell the phenol for quite a long time. They do hang around, and then if you go along and get hold of some food or something like that, you transfer that odour to the food. Dermal penetration is low, so in other words it doesn't go into your skin, doesn't last there for a long time, and from the commercial point of view, very, very good storage conditions. It lasts for a long time. Looking at disinfection and sanitization, and I'll also come up with some definitions in a moment, but not too bad. Okay, perhaps not as powerful as some of these other materials, but what I say is, do you really want your kitchen or your bathroom smelling like a public laboratory? You know, these things will work, but so will the quaternaries, provided you give them the time to work. So, definitions. There's a lot of definitions around, and I'll show you how this all fits in, but generally speaking, when we're talking about sanitizers, we're talking about a material that's going to reduce a population. It's not going to kill every bacterium, it's not going to kill the spores, but it's one particular level. Disinfectant takes it that little bit further. You get more killing of the organism. And a sterilant, these are the very, very toxic chemicals, and you do sometimes have to be very, very careful in using them. And one of my other roles in the UK is to go around and look at the health and safety of using some of these sterilizing materials. Sometimes the sterilant is so toxic that the worker going back into that area becomes quite seriously injured because of the residual sterilant. Well, that's the EPA's look on the definitions. There are other definitions that you can use. A disinfectant is when you've got very, very high populations of bacteria or fungi and soil or dirt. Whereas biocides, this is a much more modern term. Essentially, these are preventing, or any material that prevents degradation or putrefaction, and particularly of organic materials. Not only food products, but wood and concrete. And concrete will degrade with certain biological organisms. Antiseptics, that now tends to be a term used for considering infection, and particularly on body surfaces, where sterilants is now considered a term purely for areas and zones. For instance, a room, you go in and sterilize a room, or sterilize an animal house or something like that. When you look at quaternary ammonium compounds, and I'm taking one particular group of quaternary ammonium compounds where we've got two big long chains, like the dialkyls, or for example a didecyl system, with two methyl groups on the ammonium chloride. These units are in ppm, and we've got three groups of organisms here. On the left we've got the some bacteria, and not bad. Okay, there's quite a variation here, but for Bacillus subtilis, that's fairly respectable in terms of its antimicrobial action or its antibacterial action. With Pseudomonas, not quite so good, but nevertheless, you can tackle Pseudomonas, and given time, you can knock the Pseudomonas out, as we proved. In fact, we deliberately targeted Pseudomonas in a lot of our tests because it was the worst case situation. With the algae, quite superb, 0.2 parts per million. Terrific activity that for knocking out the greenness on say decking or on paths. And fungi, again, not too bad. This is the one that I was particularly interested in, the black mold that you get in bathrooms. Be very interesting for the hotel management to try this thing out in one or two of the bathrooms here. You go and have a look on the ground. It's a beautiful growth medium for Aspergillus. Gets in there, and Aspergillus, of course, in a situation that we encountered on Monday, one of the members of the audience was very interested in transplant operations, and Aspergillus on the transplant organ can cause death not only to that organ, failure of transplant, but also failure of the person who's receiving that organ. So Aspergillus is quite an important area, and the quaternaries are very, very good at taking Aspergillus out. We actually initiated some tests back in the UK about a year ago with Aspergillus, and we still have not got the mold growing on those test samples. Absolutely incredible. Right, I warned you you're going to get some chemistry. Well, here's some more chemistry. This is what a molecule would look like on a molecular drawing program. Here's, this one is didecyl, dimethyl ammonium chloride. We've got two long 10 carbon chains. There's one running down the back, one running down this side. There's the central nitrogen atom, the ammonium, and then we've got a methyl coming out here and another methyl going behind. You see that shape? It's one of these amphoteric molecules where you've got a combination of non-polar organic character and polar inorganic character. And it's this amphoteric or semi-polar system that gives it its particular properties. So if you put this material, for example, into water, it would assemble itself, and you produce these supramolecular structures. The blue circles represent the polar head units, or the ends where the charged structures reside, and these straggly bits down here, these are the non-polar tails. So put it into water and you would get that sort of system, which is known as a micelle. Very, very important for drug delivery, but also important in an industrial application as well, because if you put this sort of molecule into oil, it's inverted. So you get the polar heads, which are normally soluble in water, they assemble this way around with the tail sticking outwards into the oil. And that is in fact a very, very crucial way of delivering some drugs. But that's another story. We have the micelles, that's the important thing. And now let's look at a cell structure, because within the cell structures, you can see this one came from the one of the Microsoft programs, one of the encyclopedia. All cells contain membranes. You've got an outer membrane, you've got cell walls, you've got membranes within the organelles in there. All these membranes are in fact composed of molecules very, very similar to these quaternary ammonium compounds. They are composed of these amphoteric molecules. Again, a diagram taken off the web showing this idealized structure of a cell membrane. And in this particular diagram, it talks about sticky heads. In other words, these are the polar bits that all stick together and are pointing towards the water, whereas the slippery tails, these are the non-polar bits that all link together, like dissolves like, and in a real situation, the polar or anionic heads are in fact phosphate groups, whereas the non-polar tails, unlike our quaternaries, instead of them just being hydrocarbon chains, these are in fact peptide and glycan chains. We don't need to go any further into the chemistry of that. The main thing is that you've got polar and non-polar, and these things assemble themselves together like a flattened micelle. Now, when we start looking at particular organisms, bacteria, a long time ago, an old European German chemist called Gram developed a stain in order to identify different types of bacteria. And this classification is still used. You know, talk about gram-positive and gram-negative. Well, Gram's stain was essentially a mixture of two dyes, crystal violet and safranin. And the structures here of crystal violet and safranin, quite big molecules, aromatic systems. The blue bits are nitrogen systems, and the whole system is positively charged. So you think about positively charged systems, negatively charged polar heads in the membranes, in the micelles. You can see why the positively charged bits of Gram stain suddenly became attracted to the negatively charged bits of the membrane. So that's why the crystal violet, and likewise with the safranin, where you've got 4 components, and again with a charge spread out over the whole system, that material would also be attracted to the anionic heads in the membranes. So if you've got a whole series of anionic systems in the cell wall of the bacterium, that would attract these materials, and then you would have a gram-positive. If it was a gram-negative, you must have a different sort of cell wall, different sort of membrane, and the material was not attracted. With the introduction of electron microscopy and fairly sophisticated mass spectrometric analysis, you can actually look at the individual components in these different bacteria, and it's now down almost to the level of taking a single bacterial cell, isolating a bit of the cell wall and getting that into a mass spectrometer. It's very, very exciting stuff, and I could spend several hours talking about that. I'm not going to, don't worry. But Oh, gosh. Anyhow, the main thing is that there is a defined structure. The crucial thing is that you've got the non-polar parts with a polar part, and the cell surface in the gram-positive bacterium is very strongly polar. Not only is it strongly polar, it's negatively charged, and hence that's the binding to the gram stain. Whereas in the gram-negative bacterium, it's quite different. Well, not too different. The difference is in the multi-layer structure, and it's this composite structure which gives the strength to the gram-negative bacteria. That's why they tend to be a little bit more difficult to knock out. It's because of this layering, but nevertheless each of those membranes is set up in exactly the same way as a standard membrane. It's got lipid bilayers, it's got these things sitting together, and if we can now impinge on those, if we can perturb those systems, well then we've got a means of killing the bacterium, whether it's gram-positive or gram-negative. Not only the bacterium, we can take fungi out. Fungi are very, very similar. They just have a little bit less of the peptidoglycan layer. Viruses, different sort of system altogether. Rather than these fairly complex lipid bilayers, you've got a protein layer. This is because of the recognition that is required. And with viruses, a lot easier to knock out. The capsid shell, or the outer shell of the virus, say it's composed of protein subunits which are in different geometrical shapes. And it's that geometrical shape that gives the recognition of the virus. So that's how the immunological systems operate. But the virus has got to be able to insinuate itself into the host cell. That's why it has a different system. The virus capsid, of course, now becomes a lot easier to disrupt. It's much thinner. And that is the important thing. You know, we tend to get into a panic when we start talking about viruses, or at least certain people do. They start worrying about bird flu, dog flu, horse flu. Oh gosh, everything's flu. Viruses, if you can catch them before they get into the body, that is the time to actually knock them out. Don't wait until it gets into the body, and then you've got the difficulty of distinguishing between a host cell which is infected with a virus and the host cell that's not infected with a virus. Get the virus whilst it's on the hard surface, and that's why all this barrier nursing is being introduced in all the European hospitals to have a go at the viruses. So H5N1, you know, there was a thing in the press earlier this week, you know, it's some guy who's developed a system, or we were told he's developed a system in order to immunise against H5N1. Well, it's coming, you know, soon, perhaps a few years, but the moment you can kill virus very, very easily. Even H5N1, hot soapy water will kill a virus. You don't need to go too far with it. So what happens when a QAC interacts with a microbe, whether it's a bacterium, a fungus, algae, virus, or what have you? You get this perturbation of the cytoplasmic membrane and also the cell walls. The positive charged nitrogen, that thing that I've been emphasizing all the time, that interacts with the anionic bit, the phosphate groups, the glycophosphates, part of a phospholipid system. So like, the opposite charges, the positive charge and the negative charge, react together. They impinge upon each other. You get this electrostatic interaction. That's the starting point. But it doesn't stop there. Because of our molecule, our quaternary ammonium compound, having this amphoteric or this dual nature of polar and non-polar, the non-polar chains spread out and they insert themselves between the anionic heads so that they can join the non-polar peptidoglycan chains. And it's that insertion in those membranes that is the killing power, the penetrating power of this type of molecule. It causes the formation of micelles, not just of the quaternary ammonium compound, but the quaternary ammonium compound and the organism. Once you start to produce those micelles, you then start to get leaking or leakage of the cytoplasmic material. So in other words, the solution starts flowing out. There's a hole, there's a chink, the material comes out, and you now have leakage of things like potassium ions and so forth, and that can start occurring at very, very low concentrations. So leakage of the nucleotides, the sugars, and the amino acids, as well as the potassium ions, starts taking place fairly low down, but obviously the extent of the antisepsis is going to depend upon these three things. Everybody realizes it's going to depend upon how much antiseptic you've got there. It's also going to depend upon how many bacteria or fungi or what have you've got there. The greater the infection, well then the more antiseptic you're going to require. But what tends to be forgotten is this time element. That is very, very important. A lot of the tests that are carried out on efficacy are perhaps for a minute contact or 3 minutes contact. If you can extend that contact to 24 hours or 24/7 for weeks, you've got a much more powerful tool, or weapon rather than tool. You've got a very, very powerful weapon to kill those organisms. So, as I said, very, very low concentration levels, down to a few parts per million, you will get stasis, bacterial stasis or what have you. You'll even stop spores from producing the outgrowth. The hyphal growth will be stopped, and we've seen that time and time again. At medium concentration levels, you can then get cell death of the bacteria, and so on. Right. What's special about microbiome? I hope I've shown you that the quaternary ammonium compounds are something that's worth looking at. What have we done to the quaternary ammonium? Well, microbiome has this material that I refer to as a cyquat, a silicon quaternary. There's our quaternary group coming down here with its alkyl chain. We've got one big long alkyl chain and a couple of methyls sticking out, and then we've got the nitrogen atom there. Then we've got another chain coming out here which involves a silicon atom with 3 oxygens around it. So this is a silyloxy group. Try saying that after you've had a few drinks at lunchtime. And compared to our typical quaternary, our didecyl dimethyl ammonium chloride, you can see there's quite a close similarity in these two molecules. So that's what's in microbiome. Here is its actual chemical structure, so if you want to write it down, that's fine. It's registered. If you do write it down, you've got to be able to write down the name and say it. It's dimethyl octadecyl 3-trimethylsilyl propyl ammonium chloride. And try saying that after a drink of red wine. This material is registered. It's registered with the EU. It's registered in the biocide list. It's also registered with the EPA as a biocide, and it is, as I say, an effective material. The important thing is it's in 2 bits. This molecule has 2 moieties. The quaternary moiety that I've been talking about for the last few minutes, but also this bit, this trimethoxysilyl group. This is the difference. This is the reason why microbiome is unique, and it's the power of the microbiome. Not to kill, but to bind to a surface. It's this group that links the quaternary onto any surface. And what I've done is I've represented a general surface, any substrate. I'm sorry about the amount of information that's on this slide, but you don't need to follow the chemistry too closely. There's our substrate. It can be a whole variety of things, whether it's a plastic, a wood, carbohydrate, or whether it's a concrete, a ceramic, a metal. Somewhere or other there is an oxygenated function. So I've represented that by OH. Here's our molecule, our cyquat with a trimethoxy group. You've got 3 methoxys in there. One of those links on to this hydroxy function in the substrate. So we've now got this material bonded onto our substrate. That was one of the hooks in Nate's animation. The other 2 methoxy groups are still there, and they link sideways to adjacent chains. So you get a sideways or a parallel polymer produced on the surface of the substrate. That polymer is a silicone, right? So you've got a silicone layer with these quaternary groups sticking out from it. So you've effectively produced a polymer on your substrate surface with these quaternaries which are there to puncture the bugs. So that's our standard structure, and you can see you've now got your effectively your quaternary ammonium compound like DDAC, but it's now bound onto the surface, and that is the crucial feature of this this effect molecule. Okay, you say, so what? You've got that on there, prove that it's effective. Well, that's what we've been doing over these past several months. We've followed specific protocols, but those protocols of course have got to relate to a material bonded to an insoluble material. It may be a fabric, it may be a piece of wood, it may be a piece of concrete or plastic or what have you. There are standard procedures, but instead of the 1 or 2 minute contact, in every case a 24-hour contact was used. The organisms, a whole variety of organisms were used. Okay, the standards that you would expect, you know, the Staph aureus, the Aspergillus niger, you would expect those. Pseudomonas featured prominently because we knew that Pseudomonas was of course one of the more difficult ones. Pseudomonas, incidentally, you find in a lot of bottles of detergent. It actually eats the detergent. This is the one I'm particularly interested in, Thiobacillus group, because these are the things that cause degradation of engineering systems. These are the things that cause the sulfate reduction, production of acids in oil pipelines and in central heating systems. Okay, if you've got a small central heating system, the damage is not quite so large, but a few years ago, Terminal 2 at Manchester Airport had to be shut down for a week because they got a Thiobacillus infection in it. Substrates that we've tried, natural fibres, synthetic fibres, even the high-level synthetic fibres, metals, aluminium, steel, stainless steel, concrete, ceramics, travertine, marble, granite, you name it, we've tried it, and it sticks well. What sort of results did we get when we put this on? Remember, the 24-hour contact, even at loadings as small as 0.01%. In other words, 100 parts per million of material loaded into a concrete sample. Log reduction factors greater than 4. And the important thing was that that log reduction factor was obtained after 28 days. So not just after you just cleaned it or just applied it, not just a day after or a week after, but 4 weeks later, you've still got this fantastic reduction rate. And the data that we've got from the Hong Kong laboratory that's been doing the independent testing this week, 90 days, and it's still up at more or less 100% kill rate. That is just totally incredible. In some instances we've got a small reduction, and that was because the surface had been subject to a fairly regular washing. So, last slide. The microbium. It differs because it's got this hook that allows you to attach it to a surface, any surface. And once it's attached there, it doesn't come off. There was a whole load of other work where we were using the high-resolution mass spectrometry to show that this linkage did not break. We were detecting down at 1 part per quadrillion, million. It was so small. My dean of faculty used to say, "Have you seen any of this yet?" It is such a tiny amount of material. This stuff doesn't come off. It's tied on there. You've also got an effective biocide or sanitizer or disinfectant, and the levels, because of that time element, remember the time element I was telling you about? Because of the time element, it's there all the time, you get these very high kill rates. It's almost as a sterilant. It's very powerful. It's unique. It's only available through the germ kill operation. As Nate said, it's come into Hong Kong for a reason, and that's because we want to take it forward. Now, that's only one aspect of the germ kill production. You've got the super seal, which contains the microbium. You've also got a pre-cleaner, a post-cleaner and replenisher, and the monitor. And rather than tell you about the chemistry of those, we thought it would be far better if a demonstration was given to you as to how easy these things were used and what they did. And we've also got a biotrace machine along so you can get an immediate idea of how easy it is to knock these organisms out. So thank you, Mr. Poole, for inviting me here to talk. I do apologise if I bored you with the technical aspects, but I'm afraid that's my hobby and my prerogative as a visitor. Thank you very much for listening to me.